Welcome. This is a talk about the Versatile Video Coding Standard for the Mile High Video Conference of 2020. VVC, Versatile Video Coding, is a new standard for video compression produced by the I2T, VKEG, and ISO-IEC MPEG organizations jointly in a team known as the Joint Video Experts Team, which I co-chair. And the primary editor of the standard was Benjamin Bross. He provided the draft of the slides that this talk is based on. The VVC standard was completed in July of this year and approved in I2T as recommendation H.266 and in ISO-IEC as 23090-3, that is part 3 of what's called the MPEG-I suite of standards. It has two basic selling points, one being coding efficiency and the other versatility. I'll start by talking about coding efficiency. That is the fundamental requirement of any video compression standard, is just the ability to compress video very well. With each generation, we learn about how to compress video better, and we get increasing computing resources that we can devote to doing that job. We're roughly, we believe, in the neighborhood of a 50% bitrate reduction for the same level of subjective quality relative to the HEVC standard, which was standardized about 7 years ago. For this measure, we're focusing especially on high resolution video with relatively high bit depths, high dynamic range, and wide color gamut. So 2K and 4K and 8K picture resolutions, generally high quality video. The other selling point is versatility. Versatility is the ability to apply the standard in many applications and in flexible ways. So we have put into the design quite a few features that are specifically broadening the application space of the video coding standard. It, for example, has the ability to code computer rendered screen content or say a desktop screen sharing from a computer much more efficiently than many standards in the past, because it was not standardized just to focus on camera captured content, but also screen content as well. For adaptive bitrate streaming, it can do adaptive picture resolution changes, which is not something supported in hardly any previous designs. It can also code different regions of a picture independently and allow those regions to be repurposed for various purposes. It supports what we call subpictures, tiles, slices, and wavefronts for parallelism, layered coding and multi-bit stream multiplexing within a single video bit stream. It has a lot of features for repurposing things and for new applications like 360-degree immersive video and advanced capabilities for random access and splicing, including gradual random access with gradual decoder refresh. Looking at the history of video coding standards, they have generally followed about a decade between the major generations of standards, looking from MPEG-2, which was produced around 1992 or 1993, to AVC about a decade later, also known as H.264, to then HEVC, produced in 2013, and now VVC in 2020. So we have produced this one actually a bit faster than in some of those previous examples. Here we show a graph for the basketball drive video sequence at HD resolution of the efficiency of these different designs, how they compare over time. You'll see that the necessary bit rate for achieving a given level of picture quality, here measured by PSNR, the bit rate keeps reducing from one generation to another, again showing a substantial improvement relative to previous generations for VVC. And one thing that may be worth noting here is that many applications are currently a full generation behind today. Many products are using the AVC standard. So there's 2 generations of opportunity there to move ahead in compression capability by jumping from AVC to VVC in having a more efficient use of the bit rate in your communication channels, including the internet. This doesn't mean, of course, that there will be a lot of spare bits on the internet. In fact, something called Jevons paradox introduces the concept that actually when we use things more efficiently, people tend to want more of it, not less of it. And in fact, video has become a major demand on worldwide communication resources. It is now more than 80% of internet traffic, and that percentage keeps going up. If we look at a study done by Cisco in 2018, roughly 82% of video is now projected to be roughly 82% of all internet traffic is roughly projected to be video today. That may actually be higher now because since the COVID pandemic broke out, video has become much more commonly used for things like engineering conferences and ordinary meetings between coworkers and so forth, and for socializing. So if anything, people are using video even more today than what was projected in 2018. Another phenomenon is the emergence of augmented reality and virtual reality applications, which didn't exist a few years ago, and are showing dramatic rises in usage over time. And then further, one that I think is particularly important is the amount of surveillance video. If we just look at the average home in many places now have routine recording of video constantly happening, or at least triggered by events. Some of this video isn't even watched, but there's just tons of video being captured all over the world, and now it's become quite routine to see a video taken from just opportunistically from a doorbell camera. That's something that was not done a decade ago, at least not routinely. So the VVC standard is addressing a very important issue. Most of the data traffic on the internet could be impacted by a transition to VVC from what is currently mostly used is AVC. For VVC, we started development in, we started explorations in early 2015, a couple of years after finishing the HEVC standard, also known as H.265. And then in late 2015, we decided to officially join forces between I2T's VKEG and ISO-IEC's MPEG, and created the Joint Video Exploration Team, known as JVET, which later became the Joint Video Experts Team, still known as JVET, after we started developing a real standard. JVET started by creating what's called the JEM, the Joint Exploration Model. That was a sort of prototype research tool for collaborative development of new video compression techniques. And the JEM got about 34% bitrate savings relative to HEVC, so it was demonstrating quite an advance in capabilities. And this convinced us that it would probably be possible to create a new standard, so we issued a call for proposals in 2017 and got people from all over the world and many institutions to submit bit streams and decoded video and descriptions of their proposed technology. And we were able to compare those against HEVC and AVC anchors and see how well they performed with formal subjective testing. In 2018, we entered the formal development phase of creating a new standard, and now in mid-2020, we have finished the first version of VVC, which is quite a complete and comprehensive standard, and we're quite proud of it. We think it's clearly the best technology known today for the coding of video. In the call for proposals stage, we had 32 organizations participate, doing huge amounts of work with coding lots and lots of video content at different bit rates. And we did formal subjective quality testing in official test labs. We found that some of the test cases were giving 40% or more bit rate savings over HEVC, both in PSNR terms and in subjective quality terms. Many of the submissions, or at least several of the submissions, were beating the JEM test model. Indeed, many of them were based on the JEM with some differences in particular coding tools. So the JEM helped us lay the framework for the development of the standard, and it helped kick off the proposals process. Here are some of the results from the call for proposals stage. We have the mean opinion score measure of video quality on the vertical axis, and then on the horizontal axis are different proposals with anchors with red circles showing the performance of HEVC, gray circles showing the performance of the JEM, and the best performing proposals shown with green circles. You can see that there's quite a lot of gain, not only relative to the HEVC anchor, but also even relative to the JEM. There was quite a lot of new technology being proposed that was showing performance capability improvement. Here is just one example for a particular video called Sunset Beach in Ultra HD format. So we decided we had a lot to sort through, but what we would start with is the partitioning scheme for the video and kind of build things up from that framework. We produced draft 1 in April of 2018 and started with a quad tree with multi-type tree partitioning scheme as the root of it. Partitioning with variable block sizes and tree structures has become increasingly important over time for video coding designs. And then that became the foundation of the first draft and the first VVC test model, known as the VTM. The VTM became our reference software for VVC. Then based on the VTM, we began to test all the other coding tools individually and keep adding things bit by bit until we were sure we had the best possible package. And of course, we refined each piece all along the way to make each piece as well designed as possible. There are a lot of features in VVC. I don't have time to talk about all of them. Here on the right, we have an example of the tree partitioning for a particular video shot. And you can see that where there's more detail and variation in the source video content, you see a smaller segmentation into blocks of different sizes to customize the coding to each region of the content. Another thing worth noting is that the largest supported block sizes in VVC are bigger than they were in previous standards. There are lots of various features, but this segmentation is fundamental. We even have something called geometric partitioning mode that has some diagonal segmentations as well. So it's not all rectangles at least in the prediction stage of the partitioning. Other things that provide significant gain, well, we have the adaptive loop filter, affine motion compensation, more advanced ways of predicting motion vectors and representing motion vectors, and really quite a few different techniques. I'm sorry that I don't have time to talk about all of them, but each bit adds something for different types of video content. Some of them apply to some color spaces and not others, or some coding conditions and not others. For example, the separate tree for luma and chroma is supported only for intra slices, that is, slices that are coded independently of other pictures. But overall, it's the classic video coding design, the usual block diagram, not so much different than it was for, say, MPEG-2 or even H.261 20 or more years ago. We're just building more and more and learning more and more on top of those things to develop more and more advanced techniques. We are also using somewhat more memory and more computation. But the framework remains the same, and for anyone who really understood how MPEG-2 worked or how maybe H.263 worked, they would understand quite well how VVC works. With the possible exception of arithmetic coding, which wasn't in those, but it's also a very well-known technology that, for example, was in the JPEG standard around 1990. Here's a diagram. There's 3 separate plots here for measuring VVC coding efficiency, performance, and complexity. And I'll go through what these 3 curves are. The green curve, on the x-axis you see generations of the VTM reference software. So over time, the bit rate savings, which is shown in the vertical axis, increased where we started with just a 11% gain over HEVC with the quad tree with multi-type tree partitioning, and then added more to that until we got to about a 40% bit rate reduction for equal PSNR in the final standard, which became stable over the last few meetings. Roughly 40% gain. Yeah, and that's in PSNR. We're actually doing better than that in subjective equality. Then there are 2 other curves here. One is for encoding runtime. This is a rough measure because this is not based on optimized implementation, but we see over time the quantity of encoding time went up until it became somewhere between 7 and 10 times the encoding time needed for the HEVC standard. So it is requiring more encoding complexity, although it's providing this big gain in compression efficiency. There is also some increase in decoding complexity, which is in this last curve on the bottom. This is the factor of the speed factor, and you see the decoder for VVC takes about 1.6 times the amount of time that is taken for the equivalent HEVC decoder. Again, these are rough measures, but if you look at the advances in silicon over a decade, an 8 times encoding complexity reduction and a 1.6 times decoding complexity increase, those are manageable. If I said reduction on the encoder, that was wrong. It's a 8-fold increase in encoding complexity. Although that's just a rough estimate, encoders have a lot of flexibility in what they're allowed to do. They're not actually required to do very exhaustive searching, and the exact performance of any particular encoder is according to the designers of that encoder. When we look at this gain of 39 or 40% for equal PSNR relative to the previous generation, it's worth noting that that gain is actually even higher than it was for HEVC relative to AVC. So it's quite a lot of gain, but this is in terms of PSNR. The gain for subjective quality, which is the real goal, is actually a little bit higher than the gain for PSNR measure, and the subjective quality is what matters. Here's some of our first verification test results where we took the final standard for VVC and tested it on some ultra high definition standard dynamic range content with two different encoders. So you can see here where we have for the blue curve the HEVC reference software encoder, and then we have an orange curve, the VTM10 VVC encoder, also using reference software, configured in a very, very similar way for discipline comparison. And then finally a gray curve. The gray curve is quite interesting. It's a new open source implementation of VVC from Fraunhofer HHI. The HHI VV-Inc encoder runs about 100 times faster than the VTM reference software, but it's actually having better subjective video quality than the reference software. So that's quite a good demonstration of the practicality of the VVC design. Somebody can make an implementation that's 100 times faster than the reference code and still actually do better subjectively, or at least as well subjectively. Here we measured about a 43% bitrate reduction for the VTM encoder and about a 49% bitrate reduction for the VV-Inc encoder for equal subjective quality. Again, this is something that this is only a couple of months after the final standard was produced, and products are going to keep getting better. So the VV-Inc encoder was just the first release. There are going to be other products and probably further better releases of the VV-Inc encoder technology. But it's a good demonstration that it is possible to make a practical implementation. Switching now to the versatility goal, I'll focus on a couple of applications. One is screen content coding. A lot of videos now from animation or from screen sharing or gaming, and that has different characteristics than camera captured content. Typically in the past, video codecs have been designed primarily for camera captured video, but we have some new features in VVC. Well, actually, some of this was also in the screen content coding extensions of HEVC, but those weren't in the main profile of HEVC and consequently didn't get deployed very widely. For VVC, these screen content coding features are in the version 1 basic main profile, so they will be supported in all applications. Second application that I'd like to highlight is the adaptive bitrate streaming. Often the bitrate of a channel is measured adaptively, and the server will send you different varying levels of video quality depending on how well the channel is behaving. Well, with VVC, you can not only adapt the bitrate, but you can switch the picture resolution without having to send what's known as an iframe that refreshes the whole decoding process. This provides a great benefit in predictive coding capability when you have those transitions of picture resolution. In older standards, you have to send a whole lot of bits when you want to change the picture resolution. So here we have a resampling process that's part of the decoding process, and we were also able to build on that same resampling process for the scalability features, what's known as spatial scalability. It's really quite indistinguishable from a decoder perspective from an adaptive resolution change in VVC. Another thing I'll focus on is the 360-degree immersive video applications. Here we can have different views of the content and different areas of the content coded with different what we call sub-pictures in the design. So we may have a source video that's extremely high resolution, but have only certain parts of that video sent to any particular decoder at a time, so that a server can pay attention to where you are looking when you have your head-mounted display. For example, if you're looking around, it knows which part of the video you are seeing at that moment, and it will send you only those parts without requiring a re-encoding for customization of that content to you. This is something we call bitstream extraction and merging. There are actually quite a few different ways this can be used, but one of the basic features of VVC is independent sub-picture coding. That is, different regions of a picture that are coded independently of each other and decoded in the decoding process independently of each other, which allows a very good ability to extract things. And we also have a high-level syntax that supports this in the block addresses, so that things can be repurposed. The standard has 6 profiles in it, where profiles are basic interoperability packages, and these are quite logically nested. Maybe I'll start by building out from the center. We have the main 10 profile. That supports 420 video with up to 10 bits per sample. That is Luma and Chroma, each having 10-bit precision. For those who aren't familiar with the term 420, that's when you have the color information at half resolution horizontally and vertically relative to the brightness information for a picture. This is the way that virtually all consumer kind of video works, with the possible exception of screen sharing. Then we have a still picture subset of that if you just want to code a single picture instead of coding moving video. The still picture profile is just a single picture, so a snapshot from a main 10 profile bitstream can be repurposed as a single image. Then on top of that, for higher resolution chroma capability, we have 444 capable profiles that correspond in a very similar way. 10 bits, up to 10 bits per sample, 444, 420, or 422 picture resolution, and a corresponding still picture profile. And then finally, we have a multi-layer main 10 profile, which supports multi-layer coding with multiple independent bit streams, or scalability, or multi-view, alpha planes as auxiliary pictures, and then a multi-layer 444 profile on top of that. So it's all quite a quite logically nested structure. Currently, we're studying some new work for what happens at extremely high levels of quality with extremely high bit rates, and what would happen if you go beyond 10 bits per sample. But this is what we have in version 1 of the standard, and we think it's quite a complete package. And as I said, I think it's quite logically structured. Just to summarize, the VVC standard is a major advance over previous standards. It's coming from the premier standards bodies for international standardization of video coding technology worldwide, both I2T VKEG and ISO IEC MPEG partnered up to produce this standard. It's, I guess, the fourth generation of such jointly produced standards. And whereas today many people are using AVC, VVC is 2 generations beyond that. It provides roughly a 50% compression gain relative to the HEVC standard, and maybe a 75% compression improvement relative to AVC. So if people are procrastinating switching from their beloved H.264 AVC, VVC is a good time to think about switching, because now you're 2 generations behind. The complexity is quite manageable, maybe roughly 9x encoder and 1.6x decoder runtime increases. Those are ballpark estimates. Certainly the level of complexity of an encoder is highly dependent on choices made by the individual product producer. But on top of the fundamentally necessary feature of having great compression capability, VVC is the versatile video coding standard. It has many features in it that are provided to make it flexible and interoperable across a very wide range of applications, including features especially for like adaptive bitrate streaming, which is becoming more and more widely used as the primary way people consume their video, and also emerging applications like 360-degree video content, and new advanced features like bitstream extraction and merging. It's been very well tested on high dynamic range and wide color gamut video, and has some features that work particularly on that kind of content. It has screen content coding tools for coding animated or computer rendered video. Those things are coded very well. We finished the standard in July of 2020. I think it's already pre-published now in I2T and should be published in final form at any day now. We're working on some relatively minor extensions, but we think this is quite a strong package for the industry to start using as the new primary and best compression scheme as a format for interoperable video communication. Beyond VVC, these standards bodies are doing some work on further studies, a higher level for scalable video in VVC, studies of much higher bit depths and near lossless content coding with VVC. We'll probably have another profile or two for higher than 10 bits per sample video coding coming out in a year or two. But for most 95, 99% of applications, we think version 1 will be quite effective. We're also doing a lot of studies of potential for AI-based technology to be applied in video compression, although those have a bit more work to be done, especially in terms of complexity, but also in terms of basic concepts of interoperability and just well-defined operational nature. The AI technology is still in a sort of a nascent period, where this represents, that is, VVC represents the state of the art, certainly the state of the art of what we know how to do well and is mature for video coding today. Thank you. And if you have any further comments or questions, my email address is here, and so is that of Benjamin Bross of Fraunhofer HHI, who is the primary editor of the VVC standard. I would also like to give a shout out to Jens Reiner Ohm, who co-chaired with me the Joint Video Experts team that developed a standard. We've had a lot of very hard work over the last few years, and I'm sure that all of us in an incredibly active project to produce VVC are very proud of the result. And we're now seeing that start to show up in product technology, and more and more information is starting to be published about the standard. Lots of studies are being conducted, and I'm sure you will hear much more about it as time moves forward. There's also a website address here for HHI's website devoted to this project, where you can find other further information. Thank you.